Lesson 6, question number 15. This is a neat one. So this says, if the mass shown below is to remain stationary, which by the way means that A is going to be 0, which makes the question a lot easier, find the maximum value of F and find the minimum value of F. So it looks like we're pushing uphill. The maximum value of F would mean if I was pushing so hard that this block wanted to slide up the hill. If it wants to slide up the hill, that would mean that friction was pointing down the ramp. The minimum value of F would be if I was barely pushing at all, so the block would slide down the ramp if I stopped pushing, which means that friction must be pointing up the ramp because friction would be keeping the block from sliding. So let's do the first situation. Of course, this is a job for a free body diagram. And I'm going to be clever. I'm actually going to copy and paste this picture into my clipboard for later because I know I'm going to want to redo this free body diagram. So first of all, I have gravity down, pause, components, mg perpendicular, mg parallel. Normal force. I have this mystery force F applied, which is what they're asking me to find, and I'm pushing so hard that this block is almost sliding up the ramp. The only thing that's keeping it from sliding up the ramp is friction pointing down the ramp. Normally I'd go winner minus loser equals MA, but A is 0, so it's a tie. Really, everything up the ramp has to equal everything down the ramp. Everything up the ramp has to equal everything down the ramp. That's the maximum value of F. Now we just got to crunch the numbers. mg parallel, mg two lines is going to be sine theta plus friction is mu times the normal force. I don't know the normal force. Oh, but look. I know another force the same size as the normal force. It's mg perpendicular. Perpendicular, of course it is. And so that's where that 1660 comes from. Let's actually crunch the numbers. So F applied, and we'll call this F applied max. That's going to be M, 150, G, 9.8, sine 45 plus mu, 0.6, times 150 times 9.8, cos 45. 150 times 9. Whoop, calculator's turned off, Mr. Duick. 150 times 9.8 sine 45 plus, not minus, 0.6 times 150 times 9.8 cos 45. And there is the 1,660 newtons. If I want the minimum, so this is part A, if I want the minimum value, now what we're saying is if I stop pushing, this will slide down. So the minimum value, let's bring back my diagram here. Again, it's a job for a free body diagram. Gravity down, components, normal force, F applied. But now friction is pointing up the ramp, because if I stop pushing, it'll slide down, the mass will slide down the ramp. So friction is helping keep the mass on the ramp, preventing it from sliding down the ramp. Again, A is still 0, so everything up the ramp equals everything down the ramp. I'll get F applied plus friction equals mg. Oh, and I got perpendicular and parallel in the wrong place. You were probably screaming at me on YouTube. Sorry about that. I didn't do that on the previous question, did I? No, I got it right on the previous question, just this one. And again, I want to get F applied by itself, so it's going to be F applied, I'll minus the friction over. And you'll notice it's almost exactly the same equation as up here. In fact, if I want to, I can just backspace edit, and instead of having mg parallel plus friction, mg parallel minus friction, and I'm done. Yay! 416, which is where that comes from. Let's be clever, Mr. Dewick. Let's put that right here. Ooh. And let's even go bring that other calculation where it was the plus sign. Let's put that right there. Okay. So kind of a neat question. Depending on how hard I push, the mass will either want to slide up the ramp or slide down the ramp. And because of those, friction will change direction.